let's begin. Lipids. So the definition of a lipid is a little bit strange. Lipids are materials, are chemicals that are soluble only in nonpolar solvents, like hexane, for example. They're not soluble in water, and that defines a lipid. So the next slide shows functions of lipids, wax coatings on some plants. And you can see that on, if you look sometimes at leaves, you can see that they look shiny and water beads up on the leaf. That's because lipids are coating the leaf. So they're energy rich with low densities because, again, they're non-polar compounds, and they store energy, and they are structural components, cellular membranes. So what we're going to look at this morning, we'll look at lipids in total, and then saponifiable lipids, those that can be saponified, this reaction with strong base. There's a simple, and that's waxes and triglycerides. We're going to cover both of those. Then on complex, we'll cover just the phosphoglycerides, and the single lipids, I'll leave that for now. We're not going to cover that. And what we don't cover, you won't see on the third exam. And then when we get to non-saponifiable, that is those lipids that won't react with strong base, we're only going to cover steroids. So saponifiable lipids then contain an ester linkage that can undergo basic hydrolysis with, for example, sodium hydroxide or potassium hydroxide. So we're going to cover, most of this chapter is on triglycerides. There's a little bit on waxes and phospholipids. So simple lipids contain fatty acid and alcohol. That's triglycerides and waxes. You're going to see when we get to waxes that the alcohol is a very special, large alcohol. And then, again, we'll focus on phospholipids under the label of complex lipids. The non-saponifiable lipids, the major category is steroids. And we'll get to that at the end of the chapter. So the chapter begins by looking at fatty acids. So fatty acids themselves are not a lipid, but they're the building blocks of lipids. So these fatty acids then are long chain, 10 carbons, 12 carbons, 18 carbons long. So these long non-polar tails are responsible for the fatty, oily characteristic of the fatty acids. Now the carboxyl group is very hydrophilic because, again, of the two oxygens that are there. And under basic conditions, then the acidic hydrogen is lost. The oxygen takes on a negative charge. So it makes that kind of, they call it like the head of the fatty acid, makes it very polar. Whereas the tail, these 12 carbons or 14 or 16 carbons, and it's always an even number of carbons, that tail is nonpolar. So where we're heading eventually is to soap. So in water, then the fatty acids form these spherical clusters called micelles. And the micelles are important. You'll see micelles when we get to chapter 19 on proteins, because some proteins exist as a micelle. But anyway, the way a micelle works are that the fatty acids come together, and the heads, which again are very polar because they've lost their acidic hydrogen, now they carry a full negative charge. So these hydrophilic groups then are very polar and water-loving. And then the tails, which again are all carbons and hydrogens, so nonpolar, they're all hydrophobic groups. So this micelle exists as the heads in the outer surface, and then inside are the tails that are nonpolar. And that's kind of how soap works. So when you use soap, then the nonpolar oil or grease on your hands, for example, or your body, that migrates, again, like dissolves like, so that migrates to the middle of the micelle. And then the grease and oils are carried away in water because the heads are so polar. And so you make actually what's called an emulsion with water, with the soap acting as what's called an emulsifying agent. Okay, so let's go to the next slide. So what about fatty acids? So normally straight chains, there's no branching. Again, it's many carbons, C10 to C20. And usually, and this, you won't see an example where it's not the case. It's an even number of carbons. So these fatty acids then are either saturated, where there's no double bonds at all, or they're unsaturated and they have double bonds. So some examples of fatty acids. Now, some of these have names you, again, would probably recognize. So stearic acid has no double bonds in it. It's all saturated. But linoleic and linolenic acids have double bonds in them. Linoleic, again, has one double bond in it. So for the exam, you will not have to memorize the structure of fatty acids. You may have to show some reactions of fatty acids, but you don't have to memorize what, for example, stearic acid looks like. I'll give you that if you need to do a reaction of a fatty acid. So now looking at the fatty acids that have double bonds in them, the double bonds give the tail what's called a kink, because the double bonds are cis double bond, not trans, but cis. And the more double bonds that the chain has, the greater the kink in the double bond. So stearic acid that you see here on the left of the screen, stearic acid has no double bonds, so the chain is linear and straight, whereas oleic and linoleic have double bonds, and so they don't sit, the chain, or the tail rather, doesn't sit in just one direction, but rather there's kinks in it. And that's important for melting points. So if you look at the melting point, for example, for stearic acid, it melts relatively high, 71 degrees, whereas oleic is 13 degrees, and linoleic is -5 degrees. And that's because the saturated tails of these fatty acids, if there's no kinks in them, the fatty acid molecules can be very close to each other, very dense, making a higher melting solid. And when the tails have kinks in them because of the cis double bonds, then they can't be so close to each other because of the kink. And so you get less density, and so you have lower melting points, and they exist mostly at room temperature as liquids rather than solids. So again, the story I just told is on this next slide. Fatty acids with the double bonds, they can't pack closely together because of the shape. So it leads to decrease intermolecular attraction, lower density, and more at room temperature like liquids with lower melting points. So the more double bonds that the tail has, as you saw in the previous slide, then the lower is the melting point. And so most unsaturated fatty acids that have these kinks in them are liquids at room temperature. So on the screen, on the right side of the screen, you see some typical fatty acids, palmitic, stearic, and you see that the melting points are relatively high and they're solid to room temperature. Whereas once you begin to get double bonds, particularly if it's polyunsaturated, meaning many double bonds in the tail, then the melting points are very, very low. So, and let's just go back for a minute. And so this has great medical consequences, right? So the saturated fatty acids are found in triglycerides that are in meat products. And the unsaturated fatty acids that are, again, components of triglycerides, these are found more in fish and vegetable oils, and that's why they're healthier for you, because they don't clog up the arteries, certainly as much as meat products do. So there's two fatty acids that are called essential that the body doesn't make but needs, but both linoleic and linolenic acids can be obtained from fish and from vegetables. So linoleic is an omega-3 fatty acid, and linolenic is an omega-6. So what does that mean? So the word omega is Greek for the end. You know, there's a song, I think, or a saying that, you know, you mean you're the alpha and the omega to me. Alpha, the beginning, because it's the beginning of the alphabet. Omega, because it's the end of the alphabet. So omega is the end. So when it's an omega-3, that means from the end of the chain where there's a CH3, in 3 carbons, that's where the double bond begins, on carbon 3. That's why it's an omega-3 fatty acid. And when it's an omega-6 fatty acid, then from the end carbon, the CH3, you count get to the 6th carbon, and that's where the double bond begins. So that's called an omega-6. So so these omega-3s and omega-6s are used to produce hormone-like substances, regulate a large variety of functions. So anyway, there's some biological good outcomes from omega-3 and omega-6 that you can read about on your own. So fats then that are solids coming from animal sources, again, I said meats, and they have a high degree of saturated fatty acids. Okay. And then oils that are liquids have fatty acid components that have the kinks in them because of the cis double bonds, and they're liquids, and they're healthier for you than would be the saturated fatty acids. So again, I've stated from the beginning of the lecture that the fatty acids are components of triglycerols, or triglycerides. So glycerol, as you'll see coming up, is a 3-carbon chain, and it has OH groups on it. And the fatty acids, again, are acids, and together they make ester linkages between the glycerol and the fatty acid. Because the fatty acid components of triglycerides are so large, then the characteristics of the fatty acid really control the characteristics of the triglyceride that they're a part of. So if the fatty acids are saturated for the most part, then the triglyceride is going to be solid. If the fatty acid components of the triglyceride have kinks in them because of the cis double bonds, then the triglyceride itself is going to be an oil and be a liquid. So triglycerides then have 3 fatty acid components to them, and they don't have, the fatty acids can be the same or can be different fatty acid components. So you'll see that. So this is rarely identical, that all 3 of the fatty acid components are identical. So usually it's a mix. So you see now on left side of the screen what a triglyceride looks like. You see the ester linkages in the triglyceride, and you see with strong base that the triglyceride is saponified, glycerol, and that's the common name, right? Because it'd be 1,2,3 propane triol would be the UPAC name for glycerol. Sometimes it's called glycerol. Usually called glycerol. It would be rarely called 1,2,3 propane triol. But anyway, then the fatty acids are liberated in the saponification reaction. The acidic hydrogen is gone, and whatever the cation is of the strong base, be it sodium, be it potassium, then that provides the counterion to the negatively charged carboxylate groups that you see. So in this particular case here, then glycerol was liberated, and then 3 different fatty acid carboxylate compounds were generated that you see. Again, you should know this reaction, but you don't have to memorize the triglyceride. If I want to test you on this saponification reaction, I'd have to give you the triglyceride, and then you would provide the glycerol component and also the 3 fatty acids that are generated, just as you see here on the screen. So you must know this reaction. So this screen now is showing you the reverse of the saponification, actually, the esterification reaction, where we're making the triglyceride. And in this particular case, we're showing all 3 fatty acids and steric acid. So again, this would be an unusual triglyceride. But again, as I said before, in biochemistry, there are no new reactions. We know this reaction to make an ester. So make sure you know the reaction, but again, you don't have to memorize what, for example, steric acid is. And in this reaction, we liberate 3 moles of water. So we talked about this a few moments ago. So if you've got a lot of fat in your diet, it's it's a risk factor for developing chronic diseases, hardening of the arteries, be the common name for it. And also there's a concern because it raises blood cholesterol levels. We'll come to cholesterol at the end of the chapter. So high cholesterol is a risk factor in the development of coronary heart disease. Again, on this chapter and future chapters, I'm not going to test you on the medical or biological aspects of what we're covering, only on the biochemical parts. So you should know the saponification reaction, but you also have to know the hydrolysis reaction. Again, nothing new. Here's the triglyceride we looked at before, and now on the aqueous conditions with acid catalyst or lipase. So lipase is an enzyme. So these hydrolysis reactions can occur with either dilute acid or using the enzyme lipase. So in this case, this particular enzyme is named after the substrate that it acts upon. So the substrate being the triglyceride, and again, the enzyme is named after it. That's why it's called lipase. And what we get for products then are the glycerol, and then the 3 fatty acids. They were components of the triglyceride, and the fatty acids now have their acidic hydrogens, right? Because it's under acidic conditions, or it's with the lipase, but there's no base around to remove the acidic hydrogen. So when I test you on this reaction, you have to show the fatty acids with their acidic hydrogens intact. So unfortunately, we missed this lab. It's a fun lab where we make soap, starting with an oil. Usually it's canola oil that we use. So we react it with sodium hydroxide, again, very strong base. We heat it up and we generate sodium salts of these fatty acids, and that's the soap that you see. So again, both reactions, the hydrolysis and the saponification reaction. So, and soaps work because the oils on your skin that water can't remove, and that's why you use soap. These oils go into the interior of the micelle and the outside of the micelle where the heads of the fatty acids are charged. Those are very compatible with water. And so you flush away the soaps, rather the fats and the oils on your skin by using soap in them. And when you lather, that's a way of forcing the oils and grease on your hands, for example, if you're washing your hands. That's a way of forcing them into the micelles, into the soap micelles. So the interesting point that's made here, the last point, is that after the fall of Rome in 476 AD, right? So from year 500 on, then particularly in Europe, they lost the formula for making soap. They didn't know how to make soap. And so they couldn't cleanse themselves well. And so they had all kinds of plagues and diseases. And then during the Renaissance, in around the year 1500, and they found the formula for making soap. They would make soap by using ashes from wood fires, and these ashes contain some potassium-based bases, and they would combine that with blubber or fat from an animal, heat it up, and that's how they would make soap. So another reaction, again, these you know well, but is used with triglycerides, is hydrogenation. So many triglycerides that contain double bonds get hydrogenated by food companies. So, for example, General Foods, that makes both Crisco oil and Crisco shortening, they run hydrogenation reactions in their facilities. So they begin with an oil that has the triglycerides with double bonds in them, and then they hydrogenate or partially hydrogenate those double bonds to go from Crisco oil to Crisco shortening. But you don't want to completely hydrogenate the double bonds, or as it says here on the slide, you make a hard and waxy product. You want to make a smooth, creamy product. So that's why it's called a partial hydrogenation reaction. And you see that here at the bottom of the slide. You see a triglyceride where 2 of the 3 fatty acid components have double bonds in them. And then with hydrogen nickel catalyst, we hydrogenate some of the double bonds, but not all of the double bonds. And it says here a summarization of the cis double bonds to trans occurs during this process also. But know how to hydrogenate a triglyceride, okay? So that's kind of the third reaction so far of the chapter. The saponification, the hydrolysis, and now the hydrogenation reaction. So here it's summarized: triglycerides with hydrolysis on the left, making glycerol plus fatty acids with their acidic hydrogens, with sodium hydroxide or any strong base. Again, same glycerol, but now the fatty acids are fatty acid salts, having lost their acidic hydrogen, and the counterion is the cation of whatever base you're using, and then the hydrogenation reaction that we just covered. So waxes. So waxes are esters of fatty acids, and the alcohols are long chain alcohols, 12 to 32 carbons. And so you see what a wax looks like here. The fatty acid component is palmitic acid, and then there's a long chain 30 carbon alcohol that's used to make the ester. So actually, this is what beeswax looks like. It's actually an ester. The beeswax takes on a very waxy kind of characteristics because there's just so many carbons in it. In this particular case, 30 and 14, 44 carbons with hydrogens on them. And so it seems like a typical waxy hydrocarbon, but in fact it's an ester. But the number of carbons overwhelms the couple of oxygens that are there. So the wax then is a long chain fatty acid and then a long chain alcohol. And you should know how to, and there's a homework problem or two where you actually have to make the wax from a particular fatty acid and a particular alcohol. But again, you should know how to make an ester. Okay, phosphoglycerides are the third quantifiable lipids that we're going to cover. And so it's like a triglyceride in that there's two fatty acid components that are bonded to the glycerol, but the third bond to the glycerol is actually phosphoric acid. And we covered phosphate esters in the chapter on acids, on chapter 5 or 15. We covered that near the end of the chapter. And that was the reason why is so that you can more easily understand what's here now, that the phosphoglyceride has a phosphoric acid component and then an amino alcohol component. So look at that structurally. So here you see the phosphoglycerides with the two fatty acid components and then the phosphate, and then the R double prime that you see on the slide. That R double prime is an amino alcohol. So what's an amino alcohol? An amino alcohol is a molecule that has an NH2 group, that's the amino, and an OH group on it, that's the alcohol. So it has both functionalities on one small molecule, and we call it an amino alcohol. So these phosphoglycerides have names depending on the type of amino alcohol that's part of the molecular structure. So you see 3 amino alcohols down at the bottom of your screen. So choline is a amino alcohol where check it out, the nitrogen on actually all 3 of these amino alcohols, but the nitrogen is positively charged because it has 4 bonds. So it's a charged component of the phosphoglyceride. So if it's choline, then one on the lower left, then there's an OH group that gives it the alcohol name, and the amino group giving it the amine name for these amino alcohols. And then the simplest amino alcohol is ethanolamine, or just 2 carbons, and 1 carbon is bonded to the OH group, and the second carbon is bonded to NH3, again with a positive charge on the nitrogen. And serine actually is the third amino alcohol, and that's an amino acid. So we'll see serine in chapter 19. So you don't have to memorize what's a licitine versus a cephalin, but you have to recognize the structure of a phosphoglyceride. So here's licitine, and again, you should recognize this as a phosphoglyceride. If I show you structures on the exam and I say which one's the phosphoglyceride, you should recognize it as, again, a molecule with 2 amino acids and then a third component, which is phosphoric acid bonded to an amino alcohol. And it's the OH that's bonded to the phosphorus, again, making that's called a phosphate when it's a phosphorus ester. And then the amino groups all, again, have charges on them. And that gives the phosphoglycerides properties as really emulsifying agents, like soap would be, because of the charge on the nitrogen. So if it's cephalin, then it's a different amino alcohol. But again, it can act as an emulsifying agent because this, if you look at the structure here, you'll see there's lots of carbons with hydrogens on them. But then you also see there's lots of oxygens and you see a positive charge on the nitrogen. So you have polar components and nonpolar components to your phosphoglyceride. And that's what makes them emulsifying agents, because what you're trying to do with an emulsifying agent is to take something that's not soluble in water and make it water bearing. So the nonpolar, for example, grease, goes into the area of the micelle that cephalin is going to make that's nonpolar, and then the polar part of the molecule is going to be sticking out of the micelle and very compatible with, for example, water. We're going to skip the sphingolipids. So skip all this. And we're going to go now to steroids. So steroids look completely different than the triglycerides and the waxes that we were just looking at. Some people call this structure of a steroid 3 bedrooms and a bath, because you've got the 3 6-membered rings, and then you've got a 5-membered ring. And this is the just the simple structure of a steroid. The steroids, typical steroids, are going to have all kinds of groups that are bonded to the skeletal structure that you see. But you have to recognize the skeletal structure as a steroid. That would be an exam question. Which structure represents a steroid? And you're looking at structures with maybe 2 5-membered rings, or rings not connected the way you see them here. So just be able to recognize the steroidal structure. So cholesterol is a steroid, and you can see the skeletal structure there of the steroid. But now there's groups on the rings, and there's even one ring that has a double bond in the ring. So no need to memorize particular steroids, but be able to recognize the skeletal structure of a steroid, for example. So again, there's a lot of medical points here that are interesting. And again, cholesterol is something that you don't want to have a high level of. You want to have a lower level of it, because it can lead to hardening of the arteries. And then bile. So bile is made in the liver, and what bile does is, again, it acts as an emulsifying agent. Think about it, that so many foods that you eat are not water soluble. Yet when we digest foods, the body is an aqueous system. Somehow the foods that we eat that are not water soluble have to get into our aqueous body system. And so it's bile that helps to do that, because it emulsifies foods that are not water compatible and makes them water compatible by, again, the food that's not water soluble goes into the micelle where all the carbons are, and then you see the charges, the charge on the bile that allows it to be water compatible and then act as an emulsifying agent. So bile is emulsify cholesterol on the bile salts emulsify cholesterol. And there's something here about gallstones that you can read when you have a chance. You don't want to have gallstones. I had them, and I've been without a gallbladder for a long, long time. Okay, and then steroidal hormones. Again, the same steroid skeletal structure, but this time different groups on the rings, and some rings having double bonds. One ring is an aromatic ring, so it can vary greatly in their overall structures. And all kinds of different steroids. No need to memorize them, but make sure you can recognize them. as steroids. And that's basically the end of the chapter that I want to cover. So once again, before leaving them, I assigned yesterday 2 YouTube videos that are very good. One is only 7 or 8 minutes, another 6 or 7 minutes. So make sure you watch both of those. They'll reinforce what I just been saying this morning. I think the homework's easy. You should be doing it very easily. But again, I'll reinforce that by sending you some documents where I do some of the problems I assign. And I might even begin to do some from chapter 19 also. So again, the structure of the class going forward is that next week will be the last WebEx, where we're going to cover chapters 19 and 20 together. And you'll be assigned homework from both of those chapters. And then the last class, that will be the 3rd exam. And I'll feed that back to you. And also, either live in the WebEx, I'll talk about the final exam, or via emails, I'll send you information about the final exam. So if you have any questions on what I just covered this morning or the class itself, then please send me emails and I'll address them promptly.